Hey, welcome back to the stream. We're continuing work on pointers again. So last week we added basic support for pointers. We added their types, the ability to get the address of something and to set a pointer. And since we're running it in an interpreter, we've got a bunch of safety checks for free, basically. So for example, this program has a bug because we're returning the address of a local variable, but this is then caught at runtime, right? So we're getting like a panic message with a stacked trace. Error happens at line 10, where we dereference that pointer to a local variable, even though the memory is freed, which is really nice. So actually, this example didn't compile correctly last time because I had a bug in the compiler. The issue was here in the declarator parsing. So the C has this weird thing where types are passed in some sort of expression way. And I originally had like the top level was the pointer declarator and then the function declarator, but I had to swap the other around. So when we had something like, so declarator, something like that, this was before, this was passed as a pointer whose child is a function. So a function pointer. But correct is this is a function whose child is a pointer. So function returning pointer. And I just swapped out around and that fixed the bug. Okay, so to continue, I want to add null, so null pointers, because right now we can do 0 and this shouldn't compile. Yeah, we cannot, even though like this is the null pointer. And since we are implementing like a modern C, we actually have like the null pointer constant. Where do we have those constants? Null pointer, right? So C added a null pointer as in C, as in C++. So let's add those. So for that, we first need to add a new type, the null pointer type. The null pointer type, just like in C++, so has type is the std null pointer t, but that's not built in, right? That is just the type. If you want it, you have to use decal type null pointer. So it's a new type, but it has no type specifier. So let's add null pointer t here to the basic type. And see what else we need to fix up. Oh, I accidentally deleted something. Should add this one back. So we add a new type. Then we need to update a bunch of lengths. We can't convert its signedness. It's not a signed int. It's not an unsigned int. It doesn't have an integer rank. It has a name. That name is null pointer t. It has a type, and the type of it is, so it's like a generic untyped address. So we are codegenning it like so. So this is just the default type, type value. So this is the type of all primary types in lauf. We don't handle it in integer promotion because it's not an integer. And that's it. So that's a new type. And then we want an expression that can be used to create an object of the type, the null pointer expression. So we've got like an integer constant expression. The standard calls those predefined constants. So let's use that. Actually, yeah, let's separate it out from a Boolean and whatnot. So null pointer expression yeah, let's call it null pointer constant expression. Leave both because why not? So this is a basic node of type null pointer constant expression, inheriting from expression. So like so. We have to pass in the type because we can't construct the type value on our own because it's not owned by us. But what we can do is we can assert our other precondition that this is an elementary type node cast elementary built-in type with type kind type built-in type null pointer t, so that it is like there's only one legal value. It doesn't have any other members and doesn't store any other data because it's just generic null pointer constant. So we of course need to add that somewhere on top to the enum null pointer constant expression and update a bunch of code that uses it. So like for example here, now the first one is the null pointer constant. And then we need to update the printing code right here. So when we got null pointer constant expression, null pointer constant expression, and that should be it. Let's handle it in CodeGen first this time. So integer constant expression right here. Then we got the seed of null pointer constant expression. Hash null address onto the stack. So null. So we don't actually need any data. And then the parsing code. So we've got like a predefined constant. Okay, so part of the primary expression in the compiler. First of all, we're adding a new keyword. So keywords are defined somewhere on top, right here. Keyword null pointer, which we need to reserve this one, null pointer. And then when we're passing atom expression right here, it's integer constant expression. So let's add null pointer constant expression. Very simple. The rule is just the null pointer keyword and as a value. So we need wanted position as well, so we can get location information. And the value is a callback that returns the null pointer constant expression and gets the what's it called, the compiler state as well as the position. And then what we're returning is state as create a null pointer constant expression at the position and state as create the with the null pointer type, built-in type null pointer t. Okay, and so let's make the formatting a bit nicer. Like so, and then we're using this one when we're passing the primary expression. So here, null pointer constant expression or an integer. This is a branch like that. Okay. This means that we should now be able to do something like that. Okay, my syntax highlighting is less modern than the compiler. that we're implementing. What are no variable conversion standard? All right, I think I know why this error occurs. Missing a pointer right here. Right, so this part passes, but we do not support implicit conversions. Right, so I can try an explicit cast, but this shouldn't. Huh. Okay, our casting syntax doesn't like pointers. That's an interesting bug. Right? Yeah. Okay, doesn't like pointers. Let's worry about that later. So, conversions. Pointer conversions. An integer constant expression with the value 0. Such an expression cast to the type void. Or the predefined constant null pointer is called a null pointer constant. And we can convert null pointer constants to pointer type. So, and then we get like a null pointer that's like essentially some invalid pointer value. So let's add a function that checks whether an expression is a null pointer. Do we've got like expression function checks? Yeah, like here, like is L value bool is null pointer constant. And implement that. Somewhere. Yeah. So it's null pointer constant. So let's copy this. Right. So if integer constant. So if we're having an integer constant, I don't need to mention this here, integer constant expression e, if it's, then the value needs to be 0. Integer constant value 0. Else if auto cast cast expression. So if it's a cast, then the type has to be void, and the it has to be an integer constant expression. Let's be a bit lazy and recurse here. Is null pointer constant cast child. So this is technically not true because void star null pointer is not a null pointer constant, right? If you interpret that like such an expression only goes back to this one and not to that one. But that's like a really weird edge case, right? I wonder whether like null pointer was recently added to the C standard. I wonder whether that's actually like a defect in the standard. I'll check after the two. So let's not worry about that. And finally, the null pointer expression. As kind. Null pointer constant expression. So those are the kinds of null pointer that we're having. Right. Okay. This we can then use in the conversion function. So we can convert null pointer to pointer, right? We can convert a null pointer to a pointer. So lauf is pointer target type, and lauf is null pointer constant, the value. Then we're returning cast expression to the target type of the value. Convert null pointer constant to pointer, like so. I hate this strength ID check. You know what? Fine. Let's make strength ID happy. Okay. So now what's the error? No other conversion, right? We forgot to implement that conversion. So codegen conversion. Where was the error message generated? Line 345. No, right. So if it's the pointer or the null pointer constant, alright, we actually do need to do something. Okay, so else if lauf is pointer expression type and lauf is null pointer constant, the child of the expression. We don't want the value, right? So we don't want the value of the child expression. And push null instead. So the reason why we have to discard this value is if the null pointer constant is the integer value 0. This doesn't have the same representation as the null address in lauf. The null address in lauf actually has all bytes set. It has null has all bytes set. So we cannot, like, converting the integer 0 to the null address is not a no-up. So we have to do something at this point. It's a bit annoying because if it already is the null pointer constant, we already pushed null, like the literal value null pointer, but this will be optimized. This is because the integer 0 does not have the same representation as the null address. So we have to remove the integer constant 0 and push the correct null instead. And now the program compiles. And what we're doing here is we're pushing the null address, storing that in the local variable, then doing something with it, doing nothing with it, I mean. And so we can do something like that. And we're getting a panic because we're dereferencing null. Okay. What we can also do is something like if null pointer, which we accept for some reason. That's interesting. Oh, we are probably not handling conversions here at all. So that's another bug further to do with. What I wanted to show is that we need to handle a conversion from null pointer to bool. We don't actually have bool. Yeah, okay, let's not worry about that. Interesting that null pointer can be converted to bool, but not to an integer type. Interesting. Anyways, we don't have bools, so let's just commit. Actually, let's first test the other thing. 0 invalid address, which is correct because if we had like a local and then we are getting the address of that local, I believe, let's actually print this one out. The address of the local, I believe this will be actually 0. No, it's 1. Okay. So all right, I know what 0 is. But the point is 0, like the integer value 0, is a valid address in lauf. So the null pointer constant in lauf is not 0, it's always set. The address 0, the number 0 represents the address of the first allocation in the program, which is in this case the handle to the current fiber, not something important right now. Okay, so we can commit that. Add null pointer constant. Okay, there was a bug with the cast expression that we should fix now. So something like this should be okay. Right. So let's fix this. Compiler. Cast. Expression. Right here. Cast. This is not a type name. Actually, this is like we need to pass a declarator here, not just a type name. So declarator. Like we need to pass. Let's actually check the actual grammar instead of guessing what it is. Cast operator. Oh, this is a type name. Check the grammar. So cast expression is a type name. Where do we define type name? Type name, type of declarator, type qualifier list, type name, specifier, qualifier list, abstract declarator. Right. So the type name is type specifier list followed by an optional abstract declarator, which is abstract, and optional so that this is not a branch, so we can't. Type name is only used here. So type name in cast. So we have to pass the closing parentheses here. Okay, so the issue is we can't decide whether or not we have an abstract declarator. So we have to pass it a bit weird. So we pass the type specifier. And then we are passing opt declarator. Either we're passing parenthesized close or we're passing recurse declarator, which is abstract, and then the closing parentheses. And then we're passing type specifiers followed by an optional declarator. And then here we're passing a type name in cast. And then we already handled the closing expression. Okay. This one now needs a custom callback that returns a type, takes the compiler state, base type, and the declarator. And then we're returning the type, get type of a declarator. State.as.types of the declarator and the base type. And that should now work correctly. Is this a const type? This is a const type. No? All right, this is optional. So if we have a declarator, otherwise we return the base type. Right. And now the correctly passed the thing, and we are pushing the 0 value. Let's print that just so we can see. Pointer's null. Okay. Allow pointer types in cast. Next up, I want to implement comparisons for pointers. So if pointer equal null, then we want to print 0. Right, but we cannot currently convert. Let's actually handle the simpler case first. So no implicit conversions first. So the invalid type for comparison, right? So we got the equality operators. Both opponents have arithmetic type. We have them. Both opponents are pointers. Right. So both opponents are pointers, and we can convert essentially like either both are arithmetic types, or we are comparing two pointers of compatible types. Pointers void of something, two null pointers, null pointers with null pointer constants, or pointers and null pointer constants. So at least one is a pointer, or one is a null pointer constant. That's the things that we can compare in addition. So if is not is arithmetic. We're only doing the usual arithmetic conversions when we're having arithmetic types. Right. So let's reformulate that. If both are arithmetic, this does both equality and relational in one thing. Do they have the same constraints? Ah, interesting. So you can convert pointers with null for equality, but not relationally. Ah, I know why. Okay, I'll comment on that later. So if they are arithmetic, then we're doing the usual arithmetic conversions. Else if lauf is pointer the type, or is pointer right type, or lauf is null pointer constant left, or is null pointer constant right. Then right, so this case handles all those cases except for the check that they have to be compatible. So what we want to do is we want to check that we're having compatible pointer types. How do I do that? So we got the function do assignment conversion. Let's actually not implement the check. To do check for compatible pointer types. So we're allowing conversions between completely unrelated pointer types. Also to do prevent null pointer comparison for relational. Okay. Great. The C standard prevents relational with null because it's undefined behavior anyway. So that's why it's statically prevented here. But undefined behavior doesn't need to generate. Well, I guess if they say it's a constraint, then we should check it at compile time, but we're not doing that. That's fine. So now at this point, we are type checking the comparison. But we're not handling that in Code. Call arithmetic built-in. I should just go to the line itself in the error message right here. Okay. Else if lauf is pointer lauf is pointer so essentially we are duplicating the same check. It's null pointer constants. So null pointer both opponents are null pointers, then the null pointer is always equal. And the null pointer has the same representation as a regular pointer, so we can do that in the same way we do this paragraph. We're doing here a conversion. We're not bothering with that at the moment. 2 pointers compare equal if and only if both are null pointers or both are pointers to the same object. A function, we don't have function pointers. Both are pointers to one past the last element of the same array object. That's fine. A one is a pointer to one past the end of one array object, and the other is a pointer to start of different array object that happens to immediately follow the first array object in address space. So, okay. So the way we're doing it is we are comparing the pointers as if they were unsigned integers. And now what? Data. So we are comparing pointers like integers. This does a bitwise comparison of the address, since two addresses are bitwise equal if and only if both point to the same object. This works. So, crucially, so we just compare the bits. If they're equal, then we're equal. Crucially, we will never have this case that one object is one past last the array, and one points to a different array object that just happens to immediately follow it. And this just means that it never happens to immediately follow, right? So we always have a bit of space after the array objects logically. Okay, so now we can compare pointers. But for equality and not equality, but we need to handle inequality. So this one should also work. But this one should relational happens to work, but they should be handled different. So for relational, we're only allowing pointers. Let's ignore that. And crucially, relational comparison is undefined behavior unless both pointers point into the same array. So what this means is that we are having int a and b, and this one is undefined behavior. even though it happens to be true because A is stored before B. There's undefined behavior because they're not part of the same allocation. And crucially, this is undefined behavior we can detect because of the way pointers are implemented in lauf. So pointers in lauf are addresses. And an address consists of an index that identifies the allocation, and then an offset within that allocation. So when we have two local variables, in this case, we're having two separate allocations, one for A and one for B. And both have offset 0 because both point to the beginning of that allocation. So when we do a pointer relational comparison, we need to assert that the two allocations are the same. And only then do we actually generate the result. So what this means is we will make use of a built-in, I think. So like integers for equality. So if expression of is equality or this is not inequality, then we're comparing them like integers. Otherwise, we need to check that they belong to the same allocation before allowing a comparison. And the way we're doing that is we're actually calling a built-in. Built-in, this built-in is called lauf lib memory. I need to include that library. Memory address distance. So this returns the distance in bytes between two addresses. The addresses must be in the same allocation. So this is done by getting the distance between the two pointers, which panics if they're not part of the same allocation. And now we are comparing the distance with 0. So we're getting 0 and we're doing a sign comparison. Okay. And now we're getting a panic because the addresses are from different allocations. So what we're essentially doing is we're rewriting this one instead of doing that. We're doing b minus a and comparing that against 0. Okay, I believe this is the correct ordering of the operands. So right, so we're doing first minus second. So the one that's pushed first is maybe the sign is wrong. But we can't really test that until we have arrays. So let's add in a to-do here. So I believe this gives us exactly the wrong sign. But to test that, we need two pointers within one allocation. But this doesn't, like, we don't have no way of doing that at the moment. So clauf to do, the sign here is probably wrong. So now then at least, yeah, right, we don't allow subtraction at the moment. So now we're at least getting a to do here to remind us to check that. I'm still going to commit that. And comparison for pointers. Okay. Now the final operation we can implement on pointers is like pointer arithmetic. However, for that we first need size of, because pointer arithmetic increments the pointers like in multiples of the underlying object size, but we don't have size of. So it's interesting to see like this sort of dependency chain between language features. So instead, my plan is to add like malloc and free. However, I don't support like including the standard library at the moment. So what we actually need to do is like implement some built-ins that just implement malloc on free. And then we can write wrapper functions called malloc and free that call those built-ins. We already have built-ins like the print or the assert built-in, but those are crucially statements. They're being built-in statements. And statements cannot return a value, whereas malloc obviously should return a value. So the first plan of action is to convert the built-in statement to a built-in expression, because expression can return value. It's only a built-in statement because we didn't have expressions when we added them. An expression, built-in expression, built-in expression is an expression. So now that we also need a type. And instead of built-in statement, we are having built-in expression. So a bunch of code will break. Built-in expression, built-in expression. Let's keep the ordering. So instead of a built-in statement, we want to print it as a built-in expression right here. Here. Code gen. Need to handle that. Then we're handling the other expressions. Built-in expression, 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 expression. And then these are now built-in expressions. And this one is called built-in expressions. And then this one is no longer a built-in statement. This is an expression. So built-in expression. Callback. So this one returns a built-in expression pointer, gets the compiler state, it gets the built-in expression built in, it gets the argument expression, and crucially it also gets allocation. And then the type is currently always void because we haven't added them yet. So we're getting the void type, create built-in type void, and then we're returning built-in expression position type built-in child. Then we are parsing this one with the same precedence as a call. So where do we pass calls? It's a postfix expression right here. Now we can let's pass them as a primary expression. Built-in expression. Okay. We obviously don't have this one. grammar expression statement beginning here. Right. Oh, built-in expression. This no longer consumes a semicolon because it's now an expression. And so the thing is, the way we're parsing it at the moment, it works, but let's clean it up a bit. The way we're parsing is this one doesn't do what you want, right? It actually does. Oh, interesting. It actually does. So, but anyways, it's still not nice that we're now having like something like this is now valid and but the seed of print consumes everything, the entire expression following after it. So I believe it's best if this now gets parentheses. So this is like passed as if it were a function call. And then we also might want multiple arguments. But we get there when we get there. So let's parenthesize just to make that a bit clearer. Like so. Great. Of course, now the tests are no longer passed. So args tests integration C, and we want C lauf assert. That part, and we want that to be converted to like so in all files, and now it works. Okay. Convert built-in statement to built-in expression. Okay. And now we can add a malloc and free built-in. Built-in expression. So print assert malloc free. So what do they do? First of all, let's add them to the compiler. Built-in expression right here. So this one is called C lauf malloc. And C lauf free. Okay. Now we need to update the switches. So if we're having a malloc, this is a C lauf malloc. And if we're having a free, this is a C lauf free. And then here doing code generation, malloc. So what we want to do is we want to call the built-in malloc. Lauf lib memory. No, it's not memory, it's in heap. So let's include yet another library, heap. Heap. Autocomplete, please. Heap alloc. So heap alloc. Signature alignment plus size. So we are currently add the alignment parameter and push it. So add the alignment parameter. Malloc is aligned for any fundamental object, whatever that means. I'll just say it's 8 bytes. 8. Move size back to top. So we need to swap the top to value. size argument, which is below alignment to the top, because that's what the signature says. So we want the size at the top. So we roll this one over and then call the built-in. And for free, we are calling allocate memory. Call built-in lauf lib heap free, which just takes the address. So call free with the address on top of the stack. Great. So now the only thing left is the type checking for it. So currently we're just always creating void. So let's get the correct type here in here. If built-in wrong autocomplete, thank you. Built-in is c-lauf built-in expression malloc, then we are creating a type. Otherwise we're returning void. And here we're getting such an annoying language. So let's see now type. So we want the forest creator, or whatever it's called, c-lauf type forest node creator. So we first get voids. Get void, and then we get a pointer to it. Pointer type to void. Otherwise we return void directly and give you a semicolon. And now so we get a pointer, the malloc 8. We c-lauf malloc 8 bytes. We set that to 11. We print the value of the pointer, and then we freeing the pointer. I'm very surprised if that now just works. Of course it doesn't. Oh, right. Because I've adjusted the syntax to require parentheses. Okay. It compiled. And it just worked. Wow. So we are this pushes the size onto the stack, then we're pushing the alignment, then we swap those two, which is pointers. Then we're calling heap alloc, which gets us an address. We're storing that in the local variable. We're storing 11 into that, we're loading that, we're printing it, and we're putting it at the end, and it just works. This is really cool. And crucially, this is still fully memory safe. Right? Invalid address at line 10, because we're accessing freed memory. And we can also do something like this. So we want to free a stack variable, invalid heap address, because this is not a heap address. Interestingly, this one is also not okay, because null is also not a heap address, whereas the regular free, this is fine. So this means we can now implement like malloc by getting a size t, which is would be just unsigned int in our implementation, returning malloc of that size, and we're getting free, which just calls free on the pointer. If pointer is not null pointer, then we're calling free. So malloc free. I cannot do implicit conversion in assignment. Okay, so in principle this would work, but we're having a bunch of bugs here. But let's commit that. Add built-ins for malloc. Free. Okay. So what the hell is going on here? Invalid use of incomplete object type. Well, that's wrong. It's a pointer. So invalid use of incomplete object type because the type is not a... What the hell is that? Oh. Right. So the type here is more the base type and not the actual type. So to get the actual type, we need to call getType on the base type, like so. Okay, that's the first bug. Maybe that's all. Yeah, that's all. So a bunch of AST, but interesting, we're getting an invalid heap address still. Okay, let's commit that first. Fix parameter of pointer type. Okay. So why are you complaining that we're getting an invalid? We're getting an invalid heap address because we're freeing the same pointer twice. So that's great. What I actually wanted to test here, which is why I'm confused, I wanted to test null pointer. And null pointer can be freed because we're checking that. So that's really cool. And in case you're curious, the way this works. So in lauf, an address consists is an allocation. This is the index of its allocation, and then the offset within that allocation. And at runtime, we manage each process in the VM manages its memory in a big array of allocations. And each allocation consists of the actual pointer to the memory, its size, and then a bunch of flags. For example, we keep track of, is this heap memory? Have we already freed it? Is it still usable? What's its GC status? And so on. Because in principle, I could add a garbage collector to see at this point. So the memory has a bunch of allocations. And when we do process, and when we want to dereference an address, not here, lauf memory here, somewhere in, I believe it is somewhere in here. Right. So we can then ask, at some point we can get an address and want its actual pointer to it. And then, yeah, first asking, do we have an allocation? This checks that the index of the allocation is still valid and that its generation is still valid. Otherwise, it returns null. So if we already have an invalid allocation index, we immediately return. Then we're also checking that the source of the allocation is not const memory. So this is stuff like static global const memory. This, we cannot then get a mutable pointer to that. And otherwise, what we're doing is like a checked offset within that allocation, which checks that the allocation is still usable, that we do not exceed, want to offset its past its end, and that it is properly aligned. And only if all of those checks pass, do we actually get a pointer. And this allows us to write code like this, and like have it complain. Like this is an invalid address because the built-in that we're calling during code generation, heap, the heap tree, this, interesting, this first manually leaks it and leak sets the status to freed. It does a bunch of sanity checks to ensure that it hasn't already been freed, that it is in fact heap memory, and then it frees it. And that's just really cool. So a bunch of checks possible, completely safe, memory checked C, and it's not that much overhead. Right, it's one extra indirection that you do not deal with pointers directly. You always have to go through the allocation array. Okay, that's all I planned on doing. So next time, probably on Tuesday, we will add size of, line of, and then can do pointer arithmetic. Thanks for everybody who stopped by, and until then.